Angular velocity and acceleration. In kinematics, we introduced the idea of linear velocity to describe how fast an object moves and the direction of its motion. The average linear velocity was defined as the linear displacement of the object divided by the time required for the displacement to occur. Now, we introduced the analogous idea of angular velocity to describe the motion of a rigid object rotating about a fixed axis. The angular or the average angular velocity is defined as angular displacement divided by the elapsed time. Or in symbol, we have omega, small letter omega divided by the difference of theta divided by, I repeat, the symbol for angular velocity is small letter omega, which is equal to the difference, equal to the difference of angular displacement symbol by theta divided by the difference of time, which give us delta theta over delta t. The standard unit for the angular velocity is radian per second, although other units such as revolution per minute are also used. In agreement with the sign convention, for angular displacement, angular velocity is positive when the rotation is counterclockwise and negative when it is clockwise. So again, according to the convention of unit, consider this figure. The minute hand and the hour hand is moving clockwise, and it gives us a negative value of angular velocity. Otherwise, if it moves counterclockwise, then it is positive. So again, it is the sign convention, but it depends upon your reference or what direction you're going to set as your positive direction. How about instantaneous velocity, angular velocity? So instantaneous angular velocity, or omega, is the angular velocity that exists at any given instant. So how we measure linear kinematics, such as linear instantaneous velocity. So that's also how we get the instantaneous angular velocity by limiting the average angular velocity as the change in time approaches to zero, which give us the derivative of angular displacement with respect to time. Example, a gymnast on a high bar swings through 2 revolutions in a time 1.9 seconds. Find the average angular velocity of the gymnast. So for the direction of the swing, we have this figure. So our given is theta of 2 revolution, which give us, if we multiply this by 2 farad per 1 revolution, so our theta is equal to 4 phi rad. And also we have given of time of 1.9 seconds. So we're looking for the average angular velocity, which is equal to change in angular displacement divided by change in time. So now we have negative 4 phi rad over time of 1.9 seconds. So why negative? As is illustrated, the direction of the swing is clockwise direction. Therefore, our theta should be in negative. So let's make this theta as negative 4 phi region. Okay? So therefore, our average angular velocity is negative 6.63 rad per second. The average angular and instantaneous angular acceleration. In linear motion, a changing velocity means that an acceleration is occurring. Such is also in case of rotational motion. A changing angular velocity means that an angular acceleration is occurring. There are many examples of angular acceleration. For instance, as a compact disc recording is played, the disc turns with an angular velocity that is continually decreasing. And when the push button of an electric blender are changed from a lower setting to a higher setting, the angular velocity of the blades increases. So ang acceleration referred to slowing down or increasing its speed. We will define average angular acceleration as change in angular velocity divided by elapsed time. Or in simple, we have alpha equal to change or delta omega over delta t. So the standard unit for the average angular acceleration is radian per second squared. The instantaneous angular acceleration at a given instant is the limit of the average angular acceleration as the change in time approaches to zero, which gives us a derivative of omega with respect to time. Now, as example problem, as seen from the front of the engine, the fan blades are rotating with an angular speed of negative 110 radian per second. As the plane takes off, the angular velocity of the blades reaches negative 330 radian per second in a time of 14 seconds. Find the angular acceleration, assuming it to be constant. So we are looking for the average acceleration, which is equal to change in angular speed over change in time. Now, our final angular velocity is negative 330 radian per second minus with the initial angular velocity of negative 110 radian per second. Over time of 14 seconds, which give us negative 16 radian per seconds. So overall, as we have already discussed linear velocity and linear acceleration, how the approach on how we solve those problems in linear is also how we solve for rotational motion. The only difference is in linear, we are talking about the displacement. So the unit for displacement usually is in meter or in feet or kilometer. While here in rotational motion, we are talking about the changes in its angle. Therefore, we're more talk about the angles in radian or in degrees. So that's only the difference, but how we solve for them is the same approach. And with the guide of our formulas, the principle is still the same, so we're just going to analyze problems. So now let's have an check your understanding, solve this problem, and write your answer in the comment section.